Good morning, everybody. Today we're going to talk about a little bit of, and we're going to get our hands dirty, doing some machine learning for computer vision and audio processing. I promise that today will be both too fast and too slow. What I mean by that is that we have actually thank you all, by the way, for filling out the survey. This is sort of a snapshot I took at one point. More of you have filled it out since, but the trends still basically say the same, which is that the majority of the group here claims they are either a novice or mid-level at most topics, which means if I try to hit right in the middle of the difficulty level of the lecture, I promise that for some people it'll be too fast and some people will be a little too slow. Hopefully it can be mostly medium and right, but please do interrupt, post in the chat as we go through in case you have some confusion. And I've included in here a couple of links for people who want to go deeper later. So hopefully that's helpful for you as well. And so what are we going to do by the end of today? By the end of today, we're going to do, I'm going to click too many times. By the end of today, we're going to do hands-on keyword spotting. So you're going to train your own model. We're going to collect our own data, and we're going to recognize two words. I'm suggesting yes and no because I know that they work pretty well. But you can do whatever two words you want. Just good luck on some of them, because if you choose two words that are too close together, you will probably have a hard time. But before we actually go through and do all that, we're also going to talk a little bit about the science behind it and sort of some of the methods that you might use, just to give you a little bit more depth into what's sort of going on. And so we got a lot of things to do. We're going to start with a little bit of summary from yesterday, a little bit of deep machine learning background, and a little bit about computer vision. Then we're going to do a little computer vision exercise. Then we'll get more into tiny machine learning, embedded machine learning, and then we'll go through keyword spotting from data collection to pre-processing to training to deployment on your own phones. So hopefully that's fun. So let's dive in. And I already actually see some stuff in the chat. I'll make sure that's no questions. Okay, great. To how does deep machine learning work? So as Vijay and Lawrence talked about yesterday, machine learning is a subfield of artificial intelligence, and it's focused on developing algorithms that learn to solve problems by analyzing data for patterns, right? And this is where Vijay keeps bringing up the importance of data, because machine learning is no good without good data. And deep machine learning is a subfield of machine learning that's focused on using particularly big data usually, and neural networks. And in this course, we'll sort of extend deep learning and go even a little smaller into tiny deep learning and think about using smaller neural network models and what are the extra challenges and extra opportunities there. And just sort of summarizing Lawrence from yesterday, remember traditional programming, we decide the rules, we get an input, and the computer gives us an output. And as Lawrence was saying, this can start to get a little bit out of hand, because let's say you're trying to distinguish between walking and running. This sort of makes sense. You say, okay, if you're over a certain speed, then maybe you're running, and then we add biking and it's over another speed, and then suddenly we add golf, and I don't actually really know how to sort of start to differentiate. And so for some of these problems, it ends up being very challenging to manually write down all of the rules. And so therefore, we can turn to machine learning, which is a totally different paradigm, where instead of providing the rules, we actually provide the answers. And we provide the inputs, and then we let the computer learn the complex rules for us. So for example, in this case, as Lawrence was saying, maybe there's some binary encoding in the computer of these different activities, and it can sort of find something that's different about them in the math, and then it can just figure out that rule for us. And for those of you that are saying, that's nice, what's a neural network? So neural networks were discovered actually quite a while ago, but didn't become popular until more recently as computers became powerful enough to really do a good job. But the idea is that they're inspired by the brain. And so the brain is made up of a bunch of neurons, and each of these neurons has a certain amount of inputs and a certain amount of outputs. And essentially you have these chemical receptors on them. And as your brain fires little chemical signals, once the signal reaches above a certain point on the input, it makes an output out the other end of the neuron. And so we have designed these artificial neural networks to essentially do the same thing. So they have some amount of inputs and some amount of outputs. In this case, I have 3 inputs, x1, x2, x3, a bias, and an output. And it's designed to sort of mimic the way a neuron works, And you can kind of just smush a bunch of them together. And just like you can have a bunch of neurons to make the brain, we have a bunch of artificial neurons to make this artificial neural network. And then you can give it some data, like a cute picture of my dog, and then the neural network can learn that this is, yes, it's a dog, and no, it's not a cat. And while that's a trivial example, neural networks have proven to be very, very good at learning very complex mappings of inputs to outputs, which is why they've become so exciting and useful today. And just diving one step deeper into that neuron, what is it actually doing? Again, remember I said there are these chemical receptors usually in your brain where if you get a certain amount of input, it does an output. And so we try to mimic that in these artificial neural networks where you sum up all of the inputs according to some sort of weights. And then once you hit a threshold, boom, there's an output out of that neuron. And that's usually how they work. And when we train the model, all we're really doing is trying to find the right sets of weights and biases that make the input to the model get the output that we want. And so there's some mathematical formula that you can go through to do all of that. And when we train, we're just updating the numbers there a little bit to get it to work correctly. And how do we go about doing that? Well, we give it some data, we sort of guess the output, we see if we're right, and then we improve our model to be more correct. And that's the general training process. And this is where, again, big data has become so powerful, because if I have a lot of data, I have a lot of opportunities to guess wrong and improve and eventually start to guess right. And so you just repeat this over and over and over again. And after it's learned, we can use it for inference. So we get this model now, and now it knows, say, cats and dogs. And so we can give it new data that doesn't have labels from the real world, like grumpy cat or another picture of my dog. And you can get that labeled cat or dog. And my slides are already posted on the website, and we'll try to post the video again as soon as I can. I've included a link here to a pretty good YouTube tutorial that talks through a bit of the math behind this if you want to get into it. The long story short is it's calculus, because the neural network is some function, and we can take the derivative and then optimize it to make it more efficient. But we don't need to get into that right now. As Lauren said, we could just learn about using it. And then as you become more of a machine learning expert, you can sort of dive deeper into the math and start to tune there. But with these tools like TensorFlow and EdgeImpulse, actually a lot of this optimization is done for us automatically, which is quite nice. So you don't have to write a lot of code, and you can just make use of it. And then over time, you can start to dig deeper if you really get excited about machine learning and start to maybe choose different optimizers and really get into the details there. So that's, I don't know, 5 minutes on all of deep machine learning. So let me pause for a second and see if there's any questions in the chat. What does it mean that y equals sum is a general equation? Yeah, so the equation that I had on the slide here, this is a general equation that is often used for many artificial neural networks. And actually, really, because of the threshold, there should be a function around the input there. And so usually what you get is the output of a neural network neuron is, for a standard neural network, is some activation function of the sum of weights times the inputs plus some sort of bias. That's like the general flow. But there are lots of different kinds of neural networks that do different things in terms of their inputs to outputs. But that's sort of what a most basic neural network is. And if you know some statistics, it essentially is like linear regression plus the activation function. But again, if you want to learn a lot more about the math, I suggest checking out these YouTube videos and Googling around, because there's a lot of really great tutorials out there that kind of dive into the math. Okay, so next, I wanted to dive a little deeper, but also have a little more fun, and talk about machine learning through the lens of computer vision, building up towards what we're going to be working on later in the day, which is more machine learning, computer vision, and audio. So this one, I want you guys to vote for me. I want you to put it in the chat. What color do you think is the pants of this guy on the left and this shirt in the middle? What color do you think it is? So put it in the chat. What color you think it is? I'm curious to see what your brain is telling you today. And while I wait for a second, I'm gonna have a sip of coffee. So it looks like the colors in the chat are red, yellow, maroon, orange, things like that. That's also what my brain sees. What's pretty crazy and cool about your brain is that that shirt is actually teal if you look at the RGB color of that image, and these pants are actually purple. Now, you're right that the original image, the shirt was yellow and the pants were red. But when we've put this blue filter over it, the actual color is no longer red and yellow. It's teal and purple. But your brain is amazing and can sort of know that this picture is artificially blue, and it like de-blues the image for you, and you still see it as yellow and red. And I have one more fun example, but I use these fun examples because I'm just trying to show you how hard this problem is. You know, before we're saying, oh, we can just look at this image and find, you know, a feature, and then we're like, that's what it is. And you can look at this image, you'd be like, yeah, that's a yellow shirt, but like, it's not a yellow shirt, it's a teal shirt. Your brain is just amazing and has learned all these really cool things. So let's do one more because I think they're fun. Is square A or B darker in color? So A is up at the top here and B is in the middle. So now that you sort of know my game, which square is actually a darker color? So a lot of people are saying A. A couple people I think have figured out my trick and have said that they are the same color. And somebody said we've been trained now. Yes, you have been trained. They are actually the same color. It's pretty crazy. It takes me a really long time to figure this one out. They are technically the same color, but because of your brain wants there to be a shadow coming off of that image. So you see B is lighter because it is a checkerboard pattern, even though those are actually the same color. So this is just like another fun little example that it's like, this is a really hard problem we're solving, and the fact that neural networks can do a lot of this stuff under different lighting conditions and different sort of scenarios is, I think, really amazing. So I just want to leave that there as like a fun little note. This one I won't do as open-ended, but if we're thinking about a self-driving car, I just grabbed a random picture of a road off of the internet. And one thing we can think about, and what Lawrence was talking about yesterday, was looking at features in the images. And so one feature we might care about for self-driving cars is, for example, all of these straight lines in the picture, or straight-ish lines, curvy lines. We might care about lines, you know, because maybe we care about the lanes of the road because we're driving a self-driving car, and it's probably helpful to, you know, stay in your lane. And so one thing we can do in terms of finding these sorts of features and images is we can use something that was mentioned yesterday called a convolution. And a convolution, again, if you just Google this, there is a ton of math behind it. But essentially what it is you take some sort of filter. And so, for example, in the middle of the screen there is a random filter. It turns out that's actually a vertical line filter. So if you put in a grayscale image like the one on the left, that will sort of, if you use a convolution with it, it will sort of output the image on the right, which is basically finding all those vertical lines. And so you can imagine if we were in our self-driving car scenario before, using some sort of vertical line, horizontal line, diagonal line filter might be a good way to start to figure out where the lanes are of the road. I also, by the way, there's a link in the top right of a couple of these slides because they're based on the edX course. So this will open a collab from the edX course in which you can also play with these filters and explore convolution a little more. But this concept of using filters to find features, to then sort of find things in the picture, is exactly how people started to think about object detection historically in computer vision. And so, for example, if you wanted to like tell apart a bird and a frog, or a person and a hammer, all these sorts of objects, you can imagine you'd have to come up with some very complex set of features to try to figure it out. And so there was this challenge in 2010 that came out, and it was called the ImageNet challenge. And the idea was that they were trying to figure out how to do computer vision. And so some grad students labeled 1.2 million examples of images with 100,000 labels, or sorry, 1,000 different labels, different objects. And these are some examples here on the left. And then there was another 100,000 test items that they kept on the side. And so they gave everybody the 1.2 million, and they said, come up with your best, you know, algorithm to figure this out. And what most people did was they would come up with some sort of set of features, using things like convolutions to find vertical lines, horizontal lines, changes of color, etc. And then they would use some sort of traditional machine learning algorithm like regression or clustering to try to say, hey, if you have, these features, you're probably this thing. And unfortunately, the teams didn't do super great. They did okay. In the first year, they were worse than 50%. They were more than 50% of the time wrong, all the teams. In 2011, some teams were able to get the error rate down to only 25%. So they were right 3 out of 4 times. And then you move to 2012 and still nobody could break that 25% barrier, except for one group, which used a technique called AlexNet. And they were able to get it down to 15%. And AlexNet was the first really successful deep machine learning paper, I would say, because it really, really impressed everybody, because it sort of blew everybody out of the water and did a lot better than anybody else. And essentially all they did was they took that feature extractor and that traditional ML algorithm and they shoved it together and they said, let the computer figure it all out, right? And sort of the way they did it was exactly how the humans were doing it, but they just let the computer tweak the values. So this is sort of a graphical representation, and it might be kind of complex, but the thing I want you to take away from it is that these first big boxes sort of on the left, these cubes, are just graphical representations of convolutions. And so all they did was they set up the convolutions just like the humans were manually doing, but they said to the computer, you can pick the filter values. We're not going to hard code, look for vertical line, look for horizontal line, combine them in this way. They said, you pick the values. We're going to just set it up like how we would do it. You optimize it. And then they did one convolution to get one layer of features, and then they did another to get higher level features. And sort of this was, as Lawrence was talking about yesterday, going from like lines to finding a hand or something in the image. And then at the end, they used one of those fully connected neural networks like we were talking about before, the sort of sum of WIXI kind of thing, just to say, okay, now that you have these features, use a more standard approach to classify them. Tell me which animal is this or which object is this based on all of these features. And by letting the computer do it, the big takeaway is sort of like the computer kicks humans in the butt and wins really well. And so you see 2012, this is AlexNet at 15%, and by 2015, it was down to a couple percent. And nowadays, they're like 99% accurate, and they're amazing. By using this approach. And I think this is a nice example because people were talking about yesterday how machine learning might take away sort of the expertise of the human, but this is a good example of the expertise of the human and the machine working together, right? It took the human to design this convolutional neural network, which has these human optimized convolution things, but we let the machine help us make them better. And sort of by working together, we get these really, really, really awesome results. And convolutional neural networks are still quite state of the art for computer vision today, and we're actually going to use that today. But I do want to just make one word of caution, which is that this is a paper from around that time that I really like, which is that because the neural network is just taking that input data and mathematically computing something to the output, it's not necessarily learning human explainable things. And this goes back to the comment from yesterday about explainable AI. And that's why that's such a hot research topic, because when the computer goes wrong, we want to know why it went wrong, right? And with the first couple of neural networks, we could not. So for example, this was one of those neural networks that was supposed to find animals and images. And when it was given this image on the left of a panda, it said it was 60% confident that this was a panda. But the authors of this paper were able to compute some really evil noise to the image. When you apply this evil noise to the image, you see the image on the right, which to you or I is still a panda. I actually really can't tell the difference between the image on the left and the right, but for some reason, it just like messes with the math and the neural network in such a way that the neural network now with 100% confidence says that it's a given. So it's now more confident that it's wrong. And this is sort of a trivial example, but there have been some other examples recently where, for example, I think it was Tencent Security put a like malicious sticker on a road and convinced a Tesla to change lanes just by having like this one little sticker on the ground. And obviously, like they fixed that. This is that's not in the code anymore. But this is just an important thing to remember as we go through machine learning. It is very exciting. It does really cool things, and we have to worry about security and privacy and all these other sorts of things as we go about doing it. And somebody has a question that change the settings so only hosts can share the screen while others are sharing because your phone is having a problem. Okay, I can probably do that. Advanced sharing options, who can share, only host. Okay, you should probably now no longer have problems. And I'm sorry that your phone is screwing up. Technology, as I said, is amazing, but is not always perfect. So actually, speaking of phones, there's a really fun little thing called the Thing Translator. And I actually suggest that you open this up on your phone. I know if you're also zooming on your phone, you might have to get rid of the zoom. So hold on for 1 second. I'll just give you one more slide. Essentially what this is Google. It's a little app where they took Google's object detection API, the thing that finds all these objects and images, and they took Google Translate and they sort of hooked it up together into one fun little app. And essentially what it does is if you take a picture of something around you, what it will do is it will tell you what the object is in English. That's in the yellow here. And then in the blue here, it will also translate that word into a different language. And so you could click on the word Spanish, and I think there's 10 different language options. And Marco's put the link in the chat as well. And then on the bottom here in green, it will tell you what were the highest matches for this particular object. So it'll not just tell you what was the object, but what other objects did it think it might have been, which I actually think is really cool because you can see here, this example, I mean, it's really small, maybe you can't read it, but it's 98% sure that this is a watch, and it was my Apple Watch, but it was also 87% sure this was a picture of wood, which makes sense because it's on a wood table. So I thought we would just take 3 minutes, and you can play around and take pictures of things around you and see if it works or see if it doesn't. And I thought that might be a nice, fun little thing to explore, the state of the art here, because these models are usually decent, but they're not perfect. And the other thing, by the way, as you're playing around, is that all the code behind this is open source. So if you Google if you search for the Google Thing Translator, there's a GitHub repo that shows all the code behind how they did this, in case you want to poke into it and understand how to use these APIs as well. So I'm just going to pause for a minute and let you all just play around with it because I think it's kind of fun. And as Marco said, we probably should get some AI background music, for these sorts of moments. And yeah, let us know in the chat if you get it to work really well or really poorly. For example, I took a picture of a soda can and it told me it was a tin, which I guess is sort of correct. It's a tin can. I was it's not the best answer. Maybe it gets your computer screen. Maybe it gets confused because there's a picture of a watch on the computer screen. Somebody's saying a banana gets classified as food. Yeah, that's not the best object detection, but that's pretty good. It is food. Some people are saying can't recognize a pen, took 3 attempts on a mouse. Yeah. So this is empty water bottle is water. That's hard. Dog was perfect. Say hi to your dog for me. Yeah, so I think as you guys are finding, a lot of these machine learning models, they can be pretty decent, but not perfect. And this one I know is not Google's greatest model. I think this might actually just be an open source model that somebody created, but it's pretty decent and it's kind of fun. I think this is a fun little thing to play around with. I also think it's particularly fun when it gets it wrong if you look at the percentages on the bottom because you can sort of see what it's thinking. since it gives you the top three. This is also what happened, by the way, if anybody remembers the Jeopardy thing where they had the computer play Jeopardy against Ken Jennings, it would answer, but it would also show like its top 5 ideas on the bottom. And I thought those were always kind of insightful to see where the computer might be guessing wrong, but you're like, oh, that makes sense. Like that is sort of what it was, but it was kind of wrong. Like, yeah, it's not a calculator, it's a gadget. Well, yeah, sure, a calculator is probably a gadget. And somebody posted the GitHub link, that's great. It can detect Spider-Man at 94%. Yeah, the code is fully open source, so you can totally poke around at it. I'll let us keep playing for another minute or two, and then I'll keep moving. Your speaker got classified as flooring. Huh. I wonder how that happened. What kind of, maybe your speaker has a lot of like rectangles in it or something, so it thought it was like floorboards? I don't know. Your pen is wood. Hopefully it's a wood pen. Yeah, I think this is like a pretty fun little thing. See, that's a really good one. I like that one. A face is a face with 98%, and a forehead and a nose with also 98%. Yeah, like that. That's what I really like. That I think is really cool, right? Because that's all the things that could possibly be, and somehow in there it decided that like the whole face is more important than just the nose in there. Your Raspberry Pi is eyewear. Well, that's a bad one. Anyway, you guys can all play around with this and keep going a little bit more too in the background. I'm just going to move on a little bit to tiny machine learning, just so that we have enough time to make sure that we can get through everything, because I'm pretty sure I planned far too many slides. So I hope that was a little bit fun, playing around a little bit with vision. Now we're going to dive a little bit more into even more tiny. So we're going to talk about embedded machine learning, TinyML. And as Vijay was saying in the seminar, and Marcelo was saying, and as we were talking about a little bit yesterday, TinyML is the fastest growing field of machine learning. And the difference here is that we're talking about deploying these models onto really small microcontrollers, which are really limited computers. And so we have to consider the algorithms, the hardware, and the software to figure out how to fit these models onto these very small devices. But what that enables us is low power consumption, battery operation, so we can run machine learning all the time, like at the sensor in remote locations, and enable new features that we couldn't before. As Vijay was saying, we can now suddenly, shrink the size of a tracking collar or an anti-poaching device down to something that you can put on a much smaller animal, or is just smaller and cheaper than those giant, huge collars that they originally had. And so there's a lot of really cool opportunities to combine embedded systems and machine learning and do some TinyML. And speaking of the TinyML kits, I know there's been a couple of comments lately around like they're all out of stock everywhere, and we know the COVID-19 chip shortage is still a huge problem. But I promise we're top on the list. So Academic Network members, we will hopefully get you these as soon as they are off the assembly line. We should be getting some boxes of them to play with. Today we'll use our cell phones, but the beauty, as we'll see later, is that using something like Edge Impulse, if you've trained something to deploy on your phone, it's one click to just deploy it on the Arduino instead. And so we hope that therefore all of this stuff is super helpful and useful. So let's talk about how you do tiny machine learning. This is sort of the flow that we were using throughout the edX course, and I'll map it to the software on Edge Impulse as well. You start by collecting data. You have to get some data, right? We need some data from the real world, whatever your data source is: audio, visual, inertial, a humidity sensor, temperature sensor, whatnot. We need to collect that data, and then sometimes we need to pre-process that data to make it nice and neat and clean and easy for the neural network to work with. Once we have that data in a way that we like it, we can design our neural network model and then train that model on all of that data. And then once we have that model trained, we probably need to train it a couple more times. We need to evaluate how well our model is doing, change something about it, collect more data, do a bunch of things to re-optimize our model. Finally, when we're done, we can take our neural network model that's designed for a computer, and we can convert it into a form that can be used by our microcontrollers, which then allows us to deploy it to our microcontroller, and then we can make inferences on our microcontroller. And that's sort of like the high level flow that sort of encapsulates what you need to do for an individual model deployment for tiny machine learning. And this is what Marcelo called the what of tiny machine learning. We also have sort of the where, which we were talking about, in that most of this happens in the cloud. You might collect data on your device. You might collect data from a data source you downloaded. You might collect data from your phone. You're probably going to do a lot of the pre-processing, designing, training, evaluating all in the cloud using some really powerful cloud computers, because that'll make everything go a lot faster. And then eventually we'll deploy it onto our microcontroller to use in the field. As though, I don't know if this was on Discord or Slack or one of the other conversations, but we were talking also about ways to get training on the device. And that is a hot, active research topic. And especially if you look into tiny federated learning, like learning with many devices, I think there's been some early results on training on some of these platforms and improving on those platforms. But it's really a challenge because these devices are really small. If you're super interested in that, probably a great research topic, because nobody really knows how to do it. So it's a perfect research topic. And then Marcelo also mentioned a couple weeks ago the how, in that you're probably going to be designing your model and training your model using some high-level machine learning API like TensorFlow or PyTorch. And then there are some slightly more compact representations like TensorFlow Lite that are specifically designed for mobile phones or smaller type things that you'll use to evaluate, optimize, convert. And then you might have something like TensorFlow Lite Micro, which finally lets you deploy it all the way to a microcontroller. And often these sort of higher level things like TensorFlow, TensorFlow Lite are written in a higher level language like Python. Not always Python, but that is sort of just an example of the kind of user-friendly language. It's Python on the front end, but as we discussed yesterday, it's probably C++ under the hood. But you don't have to interact with the C++. You can just use nice high level Python. And then when you go all the way to TensorFlow Lite Micro, unfortunately there it is C++ all the way, because on these microcontrollers, we don't really have enough room to host a whole Python interpreter, and we'll use Edge Impulse today. Edge Impulse kind of allows you to do everything in Edge Impulse. There are some other services that are starting to pop up that do similar things, but Edge Impulse is a really great one. And you don't actually have to write any code, as you'll see, but you can write code if you'd like to. So you can kind of take full advantage of the advanced features of all these frameworks, but you can also sort of just click through and learn. So we think it's actually a really nice service to use, especially for today, since we have such a wide variety of backgrounds. So that is my 5-minute intro to tiny machine learning as well. So hopefully we're all up to speed. We're 30 or 45 minutes in, and now we're actually going to get to the topic for today, keyword spotting. If there are any questions, though, please post in the chat. I will keep trying to occasionally check on that. And if I don't see a raised hand, Marco, Marcelo, if you notice somebody, please interrupt me. So what is the task that we're going to do today? What is keyword spotting? Well, the idea here is not to do general speech translation or general speech recognition, or do the kind of thing that, Alexa or Siri or Google can do, that is, translate, like learn whatever you say and get you an answer. Here, we just want to recognize that keyword, that hot word, that thing that turns on your smart device. I won't say all of them because I'm sure some of you have them and it will alert your house, but okay, big space, Google, like that kind of thing, or hey, big space, Alexa, or Siri or whatnot. That actual word that turns it on, that's the keyword spotting problem. And here what we've done is we've simplified the task to selecting or identifying just a few keywords. And that allows us to use a smaller model, it allows us to use less data, and it allows us to easily deploy this onto an embedded device like a microcontroller or a bigger, slightly bigger, beefier device like your phone. And so that's what we're going to work through today. And we're going to do it using Edge Impulse, and we're going to just, for the rest of this talk, we're going to just start at collecting data and end at making inferences and sort of work through the whole TinyML flow. And I'll talk a little bit more about theory, and we'll do some hands-on work as well. Yeah, so before we actually collect our data along those lines, let's talk a little bit about how to collect good data. And this is not like the answer, this is just like some suggestions, and particularly tuned for this keyword spotting problem. If you want to go and like deploy this in the real world, please consider things like who will use your model. It's important to understand what languages people are speaking, what accents they have, if they're going to use slang, because if you train a model with all native English speakers and then you have all people with accents using it, I guarantee you it will work poorly. If you look at the edX course, there's been a bunch of like interesting comments around people with different kinds of accents having different words working better because there's a pre-trained model in there that's mostly native English speakers as just like a demo. And it works a lot better for, me than it does for other people who have a stronger accent. Where will your model be used is also really important. Is there going to be background noise? Are people going to be far away from the microphone? Are there going to be echoes? If you don't take these things into account when you collect your data, you will have a data set that works perfectly in testing, and then when you deploy it to the real world, it's going to fail because it won't be able to account for all of these things. And then other things around like, why will your model be used? So it's like, will there be a different tone of voice? Are people going to be, is this used for an emergency? So everyone's going to be panicked. You need to actually capture that in your data set. And why are you picking the words that you're picking? If you choose as a keyword, like hello, that's probably said a lot. It'll probably false trigger a lot. You'll get a lot of false positives. And also though, you need to think about what amount of false negatives are you happy with? Like what happens if it misses the keyword? Again, if it's an emergency situation, that's a problem. So maybe then you need to spend a lot more time making sure you have really, really good examples. And these are all just sort of suggestions and things to think about to help reduce bias and sort of protect privacy. I didn't really actually have a privacy one in there, but you need to think about how you're collecting your data. You can't just use people's voices all the time. That is invading their privacy. And so there's all these different considerations around bias and privacy, and we're going to luckily get to talk about this a lot more in some sessions tomorrow and on Friday. But this is actually a real challenge for this data-centric machine learning in how do we collect good data sets that are not biased in ways that are okay and don't invade people's privacy. So for keyword spotting in particular, pick uncommon words. This is why I think it's not just Google as your keyword to turn on your Google Home. It's OKG because I assume they did a bunch of testing, and if they just used the word Google, I'm sure it would turn on all the time. But I guess a lot of people don't say okay, G, and then therefore that's actually a bit more uncommon. I think that's why Alexa is Alexa as well. I think Alexa also has some like really unique syllables in there. So it's very clearly that word. So things like that are good things to think about. You also want to record a lot of other words. If you only ever give it examples of silence and your keyword, it will probably learn that anybody talking and saying anything is your keyword. And so, you want to include a lot of distractor words. So if you were doing Alexa, you might want to also do like Amelia or, I don't know, X-ray or some other things that sound kind of similar to teach it exactly what your keyword is and not just kind of what the keyword is. You want to record in the location you're going to be deploying. If you're going to use this out in the real world where there's a lot of wind, you might want to go record out there so you can capture that. If your end users are going to have lots of different ages and tones of voice, you're going to want to get that into your data set. You want to use the same hardware you're going to deploy on. If you're recording on your computer and deploying to your microcontroller, which is a different microphone, which is the flow that we actually did just for simplicity in the edX course, a lot of people noticed that there was actually bias coming from the difference in the microphone there, which was actually causing lots of issues. And, test, and improve always. Somebody was asking if a key phrase could represent a keyword. Absolutely. it would just be a slightly longer thing that you're going to record. For the purposes of today, we're going to cheat to make the demo more likely to work with very little data, because we don't have a lot of time, because Google and Apple and Microsoft and Amazon have like billions of samples of words, and we have time to do like 30 or 40. So I strongly suggest you stay in one spot, only record yourself, use a very common word that's very easy to tell apart. I like yes and no because that S sound is pretty harsh, and usually, even if you design a bad model, it can capture the yes, even if it doesn't capture the no. And if you're only recording yourself, just test yourself for today. Just do something simple, cheat a little, make it work. It'll be more fun because it'll hopefully work a little bit, and you can go from there. I did test this myself, and the model that I did was pretty good on yes and was not so great on no, but it worked okay. And given that we're going to do this really quickly in the next hour, I think it's not too bad. But data. If you have fun today and you want to make it a lot better, go do all those things I talked about with data. Go collect it from all your friends and make it more general. One other quick note on keyword spotting. How do we actually design a testing scheme that works well? There's actually a lot of things that could go into getting a really good testing scheme, but the one I want to point out is that often what you do is you take your original data set, and this is what Edge Impulse will do automatically for us, and split it into a training set and a test set. And sometimes you actually even split it into a training set, a validation set, and a test set. I think for today, we're just going to split it into two automatically. But the idea here is that if you are training and improving your machine learning algorithm on some training data, the algorithm is going to learn the training data, and you want to make sure that it hasn't just memorized the training data, but it has actually learned whatever is the underlying features about that data that generalizes. And so that's why you want to then occasionally test it with an external set of words, in this case, or pictures or whatnot, that it hasn't seen before. And so that's why often you'll split a validation set to improve during each training cycle, and then a final test set that you hold out and you don't let it see until you have the final model to get a really good independent performance estimate. And so what we'll see today, I think, is just it'll say when you collect data, it will automatically split it into training and test. And then during the training, it will use the test as the validation. But it's basically, there is an independent set because you really want to make sure that you're not just memorizing your training data. This is a problem called overfitting. We don't really have time to talk about that today, but long story short, get an independent test set. It will make your model a lot better, or it'll at least give you a better sense of how it will work in the real world. Because the assumption here is that if you've done a good job collecting data, then this now independent set of data does a good job of representing what a real world test would be. Is it recommended to use a test set as a validation set? You can you can just use two, yes. Some people like to keep like a super test set if they're going to do a lot of reruns of training, because then you sort of have, if you are tuning your training based on your validation set and your training set, then sort of you've kind of corrupted your validation set a little bit, but you can do that, and that's what we're going to use today. Can you do hello world? Yes, but the longer the phrases are and the less different they are, the less likely it is to work. But I honestly, do whatever you want. Go nuts, try it. This is just for fun. So have fun seeing what you can do today. So yeah, with that, we're actually going to go and we're going to collect some data with Edge Impulse. Before we actually do it, I just want to map the little framework that I had to Edge Impulse's stuff so that you're not confused as we go through it. So Edge Impulse uses sort of 4 steps. It says dataset, impulse, test, and deploy. And the impulse sort of subsumes pre-processing, designing, and training your model. So it's all the sort of like cloud operations to get to a model. And that's really the only difference. So that's sort of how we'll do it today. We'll collect the data set, we'll design an impulse, which means we'll pre-process, design, and train our model. And then we'll test it and deploy it onto our phones. If you haven't created an Edge Impulse account yet, you should create one now. go to edgeimpulse.com or studio.impulse.com/signup. But I think if you just go to edgeimpulse.com, you can also just like click to sign up. You'll probably have to validate through your email, and then you should have a free account, which should let you create your first impulse. We're not going to do anything crazy today, so the free account should totally work great. I know there are other upgrades if you want to do other things in the future that you can do, but that should just work well for today. And I think if we can put the link in the, Sebastian already put the link in the chat. Thank you, Sebastian. So I'm going to keep moving a little bit, but if you have to create your account, grab that link out of the chat and do that. And does EdgeImpulse use TF Lite Micro? Yes, it does. And we'll get into that later. You can actually write just TensorFlow code and it will totally work. Or you can use their graphical interface, which is pretty awesome. So when you get into your account, oh, and by the way, remember these slides are all posted. So if at any point I move too fast for you and you want to go back and look at the slides, they're all on the website on that schedule. I think it's actually this exact version because I posted this pretty late last night. So what we're going to do is we're just going to create our own project. So if you click on your like name once you log in, you probably won't have a bunch of projects that you've been playing around with. They probably just say create new project. But we're just going to create a new project to start. And when you create a new project, what you're going to get is this thing on the right is going to be on the left. And this is sort of the EdgeImpulse dashboard flow. And this just maps directly to this process that we were talking about before. You have data acquisition, impulse design, then they have a bunch of really cool things you can do for testing, which we won't have a ton of time to explore today, but I do suggest you explore at some point. And then there's a button for deployment. And so we're just going to walk through this thing on the right, which is essentially the same flow as what we've been talking about the whole time, and go through and do this together. You can use EdgeImpulse on your phone or on your computer, and you can open up Zoom on your phone or your computer. I think I would suggest that you collect data with your phone so you can deploy to your phone later and use the same thing. So if you have two devices, it might be easier to click through all the stuff on your computer so you can see it a little bigger, and then like record the data on your phone potentially, and like minimize me and just listen to me, because there'll be another break to collect the data, and I'll give everybody like 10 minutes and whatnot. But please, again, post if you're falling behind, have questions, whatnot. So what we're going to do today, I'm going to walk you through the steps, and then you're going to go do this, but I just want to tell you where we're going. You're going to collect probably about 30 samples of 2 keywords. I'm suggesting yes and no, but again, you can do whatever 2 keywords you want. Also, you're going to want to collect 30-ish or more samples of some unknown words or background noise or static or whatnot. This is really important. If you don't do that, the model is going to get super confused because it's not going to know, it's going to just recognize silence as things and whatnot. So it's important to give it a bunch of examples of what is not yes or no, so it can figure that out as well. And so what we're going to do is when you go to EdgeImpulse, right, you get this sort of flow down here on the left, and this is your dashboard. And right in the beginning, it's going to say, you know, like, let's collect some data. And if that doesn't work, you can click on data acquisition, and it's going to go back to let's collect some data. There's a couple ways you can do it. If you're already on your phone, if you actually collect the use your computer button, it'll open it up on your phone. If you're using EdgeImpulse on your computer, you can click on show QR code, and then you can scan the QR code with your phone camera, and then it will open it up on your phone. Either way, I found the phone to be like a really easy way to collect the data. So I sort of suggest doing it that way. And what's going to happen is it's going to pull up a web page that looks something like this. And we're going to be collecting audio today. So you're going to click on collect audio, which is going to open up another page that looks like this. And if you click on the label, you can actually type in whatever your keyword is. And then you can click on length to do the length. And I would leave the category as just split. That means it will automatically do the training and testing split for you to keep it simple for today. But in the future, you could actually manually decide how to do that. So you should change your label to one of your keywords, do a bunch of recordings, and then do the other one. And if you have some questions, if you have another browser window you can open up. There's a lot of tips for using your mobile phone on Edge Impulse, and actually they have really great documentation in general. So if you look through their documentation, it should probably answer a lot of questions, but then again, please post the chat, please do whatever. And so, and when you're done, if you click on this data acquisition tab, you're going to be able to see all of your samples. So if you accidentally record something you don't like, you can click on the 3 dots next to it and delete it. If you accidentally record some that are 3 seconds and some that are 2 seconds, you can go in and crop the shorter ones down. It is important that they all end up being the same length. It makes it very hard for the pre-processing and neural network stuff to work correctly unless they all are eventually the same length. You can crop them, you can split them, you can change labels if you accidentally labeled something incorrectly. You can listen to them and say, I don't like that one. You can do all this sort of kind of stuff with it when you're done. And so what I would suggest is, take 10 minutes. We'll take a quick break. At the same time, collect 30 samples of each of your 2 keywords. Again, suggesting yes, no, but you don't have to. I found that 2 seconds is a good time to have enough time to click start, see that it started, and then say the word within that time frame. And make sure you also do some unknown words. And go nuts. If you want to do 100 samples, do 100 samples. I'm just saying at least 30, because that is probably enough to get a model that's okay for today. And with that, I think we need more AI background theme music. Or probably not, actually, because you want to just record and you want me to be quiet, so you can do it. What are the category differences in data collection? Oh, so the categories are just the 3 different words that you're using, yes, no, unknown. And the point there is that's you labeling your data so that when we train the model later, it has the recordings with the labels, and so it knows which is what. And that's really important because remember, when you train a machine learning model, you have to, with this supervised learning approach to training a machine learning model, you have to give it the data with the labels so that it can then learn the mapping so that it can do it again in the future. Can you share data with other Edge Impulse users? Yes, you totally can. I will post to Discord later. There's actually a way where you can sort of just crowdsource all of it. I was playing around with that, and I found for a demo like today where we're only doing about 30 examples per person, it works better if you just do yourself in terms of having it be successful. And it's very easy to make a project public, and you can share the link, and you can have all your friends do it if you want to quickly collect data. Somebody's also asking about the training test split, the automatic 80-20. That's a great split. I would just leave it at that for now. It's just a nice way to get a lot of training data and some of your test data and not have to think about it. That is just a base level. I'm sure you could, if you were recording thousands of samples, you could probably get away with 90-10 or 95-5 or whatever it is. Essentially what you want is to have a decent amount of training data and then enough testing data that it's actually reasonable. So if you only had 1 test example, that's not really fair to yourself, because that could be a particularly easy or particularly hard example. And so if we're only collecting 30, 40, 50 of each, 80-20 is a good option for now. Yeah, but the beauty of Edge Impulse is, right, it's very easy to do this right now, but it can also do so many more complex things as you dig into it, so you can kind of do whatever you want. And I basically tried to set this up so we could do as many of the defaults as possible and not have to do all the advanced stuff, but you can. Can we have the link in the chat? You mean the link to, the using your mobile phone link? Yeah, I think I can put that in. Oop. Oh, that was a direct message. Post that to everyone. So yeah, take 10 minutes. We'll resume at 15 after, and go ahead and collect it. It gives me an error when I try to allow the microphone in my phone. Huh. I haven't seen that before. One thing you could try, Diego, is maybe going to your settings in your security, you might have some like never allow access thing in your phone. And so I would check those security settings. If that totally fails, you can also record on your computer. If you have a computer or iPad or laptop or whatever, in a different way. But yeah, I would suggest going to your security settings. Oh, Marcelo says he had this problem with iPhone 6. So you may have to manually enable audio collection. I don't know if Marcelo has more. I would private message him. He might have more thoughts. So as we get back, I just want to answer 2 questions that I've gotten. So one, if you get a error that says something like failed to upload, payload is missing, it's probably because you're being too quiet. I found that if you are then a little bit louder, that sometimes works better. And then the second one is, after recording, should I press switch to classification mode? No, that is for deployment much later, but we're gonna have to pre-process and train our model first. So you can just leave it there. You can leave that screen up, or we can come back to it later to press switch to classification mode. And we'll get restarted in a second, but now my taskbar has popped up. So I just want to get rid of that really fast. So just give me 1 second. Go away, Slack. And go back to share. Okay, so I hope everyone was able to record some data, and I will be very curious to see at the end how well that worked for everyone. But we got a lot to do before we can actually test our model and switch to classification mode. We have to pre-process our data, we have to train it, and then we have to do some testing and deployment. So to dive into pre-processing, I thought, again, I'd start with a little bit of background on pre-processing, and then we can do pre-processing and training using Edge Impulse. So, right, we've collected our data, check. We're gonna move down to impulse design and pre-process our data. So you might be saying, well, why do we want to pre-process our data? Why can't we just send that raw data to the neural network? And the answer is that sometimes your data will come in a form that is a little hard, potentially, for the network to understand. So for example, this is 2 signals of a yes and a no that I recorded much earlier for the TEDx course, but it could be the samples that I recorded today for this. And to me, both the yes and the no look very similar. Like there's a little bit of difference. Like this yes over here looks like it might have like a bigger tail, but they're not that different. They kind of just look like, oh, you can't hear me. Can anybody hear me?
No, it's
Yes.
okay.
It's okay. Yeah, it's fine.
Okay. So that's just one person's problem. Okay. I would suggest you mute and unmute and switch your audio device. Good. Okay, cool. I thought my computer was having a malfunction again, which is not too uncommon because technology. No worries to whoever that was. That's a very, very good point. It really could have been my mistake. So anyway, I can't really tell these apart, and so there might be some pre-processing we want to do that might make it easier for the computer to also tell them apart. And so one thing we could consider in terms of audio is sort of what are the different components that make up this signal. And so, for example, most audio signals are actually made up of some combination of smaller sine waves. There's different frequencies, different pitches in your voice. And so the question might be, for this particular no, like what are the different signals that go into it? And maybe could that actually make it easier for us? And it turns out that there's a lot of research actually on this from the audio recognition speech processing field. And again, I think there's been a question before that was sort of like, what pre-processing should I do? And the answer is you should actually really go search for the domain experts here, right? Like I'm not, and my research area is not audio processing. I've been told that this is a good way to do it, by all those experts. And so that's sort of the approach that I'm going to take. And so one of the ways to do this is by using something called a fast Fourier transform. I'm not going to really get into the math of it today, but essentially what a fast Fourier transform does is it takes the signal, which is sort of just like these spikes of amplitude over time, and it breaks it down into the various frequencies that make up the signal. So if you have a higher pitch voice, you'll have more frequencies at higher frequencies. If you have a lower pitch voice, you'll see more lower frequencies, and all the different words that you say have different patterns of frequencies in them. And one thing you can do is you can actually, take a slice of this time signal and convert it into its FFT, and you can get these frequency domains. But what's actually more powerful than just getting the frequency domains is that if you actually take lots of little overlapping slices of your audio signal, these little overlapping red boxes, and get all the FFTs and then stack them up, what you end up is with this thing called a spectrogram. And this spectrogram is what we ultimately is something that we want. And what you have here is you have sort of the time going along one axis, you have the frequencies going along the other, and the color is sort of the amount of that frequency that you have. And this sort of encodes some sort of image, in a sense, the spectrogram of this frequency. And this is actually quite nice because if you look at those signals I had before, the yes, no, I actually also had a quiet one. And to me, like the quiet ones look the same and the loud ones look the same. And like I can tell those apart, but I can't necessarily tell apart what's a yes or a no. But if you look at the spectrograms of quiet or loud actually look much more similar for the various words. And especially if you look sort of in what I've kind of highlighted, you can see sort of that like the yes has like stuff in that like lower box there and the no kind of doesn't. Right. And so that might be some sort of fundamental difference between yes and no that you can kind of see in the image. And therefore, it's probably easier for the computer to tell it apart as well. And this is sort of the kind of suggested approach to sort of going about thinking about audio is to get it into a spectrogram. And actually, we'll do even one more step on top of this in a second. But I kind of see a question. How can I choose the right signal decomposition technique? Again, actually, for your various signal, I would really actually just look in the literature for what various experts are suggesting. The spectrogram thing actually tends to work quite well. In a lot of cases, it's not necessarily always the correct answer. And just like in computer vision, where there were researchers using convolutions and then manually combining them before deep learning came around, in audio, there were researchers using spectrograms before deep learning came around. And so we're just building on top of that knowledge. And so I would go and try to find the experts in your domain of interest and figure out what they're doing, because they're probably doing something really good. And then we can build learning on top of that. And that tends to work really well. But we can actually go farther than a spectrogram, and we will today. But I want to pause for a second and say what's actually another beautiful thing. And the reason why I was calling spectrograms images is you can just treat them like an image, and we can then actually pass them into these convolutional neural networks, which is great, because then we can build on top of all of the image processing stuff that's been researched and figured out, and just use these images in here, which is why we're doing image and audio today. But we can actually take a step further. Can we do better than a spectrogram? Can we actually take even more domain knowledge into account? And it turns out for human speech, we know actually some of the limitations and abilities of humans. There's a lot of research on sort of like what frequencies humans hear and what frequencies humans can tell apart. And it turns out, again, there's more math that you can go ahead and Google, but there's these tools that we can just use that do it for us. So I'm going to try to like land in the middle, but humans can tell apart low frequency noises a lot better than high frequency noises. And so there's this idea of MEL filter banks, which actually sort of like compresses your signal at high frequencies and grabs like a bunch of it and sort of compresses that down in the spectrogram. And then at lower frequencies, it does less of that, and it keeps them more independent. And this is actually a good representation of how you can tell apart words. And so if we apply this, what they're now calling an MFCC, if you apply this transform to your spectrograms, what ends up happening is you get a much cleaner signal, which you can see on the right. And it's also much more representative of what a human can hear. And actually, the part that I wanted to highlight is, again, that sort of yes-no difference area. To me, it's actually much clearer that the no and the yes are different here on the right. And that's sort of the hope, right? Is that we can go through this pre-processing to get to something that is actually more different, that then when we pass to our neural network, it'll be easier for the neural network to tell it apart. This is not to say that you couldn't just take the audio signal and pass it into a neural network. You probably could, and it probably could learn things. But building on top of the domain experts in audio signal processing and jumping to this MFCC, that actually saves us a ton of time, makes it a lot easier to learn. And there's another Colab link from the edX course that kind of allows you to play with subsignals and do the spectrogram MFCC stuff in Python. Now, again, one quick warning. Whatever preprocessing you do in Python to do training, you must also do in C++ on the device, right? Because if your model only knows MFCCs, you have to give it MFCCs. You can't just suddenly give it a raw audio signal or it will go, I don't know what this is, right? Because you trained your model on some kind of input. The good news is with Edge Impulse, we can actually sort of kind of do that automatically. They have a bunch of built-in ones, and they have a process for adding your own custom pre-processing as well. And I think I kind of broke one of my slides, but all that was supposed to be behind here was sort of like, you can also denoise and you can do lots of other different kinds of pre-processing. But whatever pre-processing you do, whatever you do for training, you must also do when you actually run the model, because you've taught the model to learn that sort of pre-processed input. So that was like, pre-processing in 10 minutes. That's way too high level, I know. And there are some people like, you want to get a lot deeper. But again, I think the challenge here is that for your particular problem, it's actually about getting deep in your particular domain to understand what are the current state-of-the-art approaches, so you can build off of them. I'm a big fan of like, use what we've already figured out as humans first, and then put learning on top of it, and don't just ask the machine learning model to do everything. I also have a robotics background, so I have some bias, and like I like the machine learning papers that use like physics and then build machine learning on top of it. They seem to learn a lot faster, work a lot better. So I just have a huge bias in terms of all this kind of stuff, in terms of, find your domain expert, get those traditional techniques and build on top of it if you can. And that to me has always seemed to work a little bit better. So with a little bit of that out of the way, I think we'll go on to some hands-on pre-processing and training with Edge Impulse. And so what we're going to do is we're going to create that impulse, right? Because the impulse includes the pre-processing and the training. And so if you go back to Edge Impulse and you click on Create Impulse, you'll get a screen that looks like this. And you'll see on the left is sort of, it's talking about your time series data, and then you have a processing block, and then you have a learning block. And from there, you can go through and do the learning. I think if you did 2 seconds, you want to up this window size, but I got it to work where it was, so maybe we can just leave it. So what we're going to do first is we're going to add a pre-processing block. So we're going to click on Add a pre-processing block, and you'll see that a bunch of these pop up. And as I was saying, like Edge Impulse has built in a bunch of different pre-processing. You can see on here is a spectrogram down at the bottom. There's this MFCC at the top. There's also an MFE, which is a different kind of MEL filter bank thing for non-voice audio, right? And so we're going to add the human voice audio MFCC one. We're going to click add there. If you actually scroll all the way to the bottom, there's an option to add a custom block. And they have a whole documentation over here. And I will actually copy this link and put it in the chat in case it's helpful for people later. There you go. Nope, that was a direct message. Man, failing at the chat today. But you can create your own blocks. You can actually use multiple blocks. You can do multiple layers of processing. And I believe the stars are just recommended. So what's nice in Edge Impulse is it will, based on your data, it will try to like auto figure out what you're doing. And it will start to recommend for you what you probably should do. Or what it thinks is like a good default setting. This doesn't mean you have to do it, but it is a nice place to start, especially when you're more of a beginner on all of this. And for the purposes of today, I'm kind of just going through all the stars and just trying to get something that works okay. So you can click Add there, and that will add this MFCC block in. It's not initialized. It's just like, that's what we're going to do. And you can see below, there's another like add processing block. And so you could add another one, but for today, we're just going to leave it at that. We're going to keep it simple. And then we're going to also click to add a learning block. And again, there's going to be two options, and we're going to go with classification. The reason we're using classification is that we're trying to classify two keywords or an unknown. And that is the problem we're trying to do. We're not trying to output some numerical value, which is what regression is used for. And when you click that, you'll get some default neural network added into there. And again, you could cascade neural networks. You could do lots of different things, and you could go crazy. But again, for today, we're just gonna do an MFCC, do one standard neural network, and we're gonna click save our impulse, and that's gonna sort of generate. You can see on the left that we have now created our impulse, and now we have an MFCC and a neural network classifier, but we have to actually initialize those things. Can you put your own model in the learning block? Yes, and I'm going to talk about that in a minute. Is an FFT-like convolution for audio? Sort of, not really. I mean, it really, an FFT is it's doing the same thing in that it's helping us find features, but an FFT is this particular thing that finds the frequency breakdown of an audio signal, right? And so it's a true mathematical thing that is decomposing our audio signal into this frequency domain. And then when we stack them up in a spectrogram, we can then use a convolution to filter that image to find our features. But it is doing some sort of like pre-processing thing to expose interesting information to us. So in that sense it is, but it is a true mathematical transformation from the time domain to the frequency domain. So there's like a very specific like math behind it. I think actually, I should have gotten a YouTube video for that. I think there's a really good one also from the same guy who I linked the neural network to. It was like 3 brown, 1 blue, something like that. He has a really good video on Fourier transforms that I think explains it better than I ever could, or better than I've ever had it explained in any course. So it's exposing the frequency domain. It's not really filtering it in any way. I hope that sort of makes sense. Oh, it seems like Marcelo is also answering in the chat. Thank you, Marcelo. Okay, so hopefully we're all on the same page now. Okay, so we have our base impulse set with some default settings, but now we're going to update it. So first we're going to click on MFCC. And that's going to bring us to this page. And here, actually, if you look on the left, there's a ton of different features you can do. There's a bunch of different settings you could set. I'm not going to change any of the defaults for today. But again, if you were an audio processing expert and you knew all these things about audio processing, or you talked to somebody, you can actually go through and change the values and set it and do sort of all the behind the scenes deep changing, which is why I really like Edge Impulse, because you can do all the customization, but you don't have to. So for today, we're just going to click on Generate Features over here, and then you can click this green button to generate your features. And that's going to actually take a little bit of time. It's actually going to run for a little while. And so while that's sort of running, I thought I would just talk a little bit about what's going to output and just sort of keep going like in the background while it's running, and then we can actually catch back up. So that hopefully should be running for you down here, like on the bottom left. On the right at the end, you'll get this Feature Explorer thing that comes out. What this is just a 3D representation of your data. I didn't do such a great job with my recording, so this is kind of muddled, and the classes look like they're kind of mixed up, which is probably why the model didn't work super great. I have seen somebody do a much better job at finding separate data, and you would hope that your Feature Explorer maybe looks something like this, where you can, really see that the two classes are very, very separate data. But just because they look similar in this 3D space doesn't mean it's not going to work. My model actually worked really great for yes, because the separation could be like concentric circles, and that's hard to see in 3D. But the Feature Explorer is a really cool thing, I think, that Edge Impulse has that lets you at least just try to visualize what the difference is between your data. And try to sort of see it apart. Somebody says they have 4 classes, no, unknown, unknown. Because you spelled unknown differently. Is this a problem? Not necessarily, because it will try to split. Now you have 2 unknown classes that it's trying to learn, and you did make the problem a little harder. One thing you could do is you could go back, clicking on data acquisition, and find the unknown that's misspelled. And change the label by clicking on those 3 dots. That's like way back in the slides. I don't think I can get there really fast. You could change the label and then redo the feature generation, and it will fix that for you. You could also plow ahead and see if that works. It could be a thing, and if you said you didn't change the label, then that was a corruption on the internet. And sorry, but you could go and change it now. Or you could plow ahead and see. I think it will probably work better if you do change it, but you don't have to. So I'm actually just kind of curious, did the feature generation finish for people at this point? Doesn't really matter. I'm just curious if somebody could throw into the chat whether or not they're done. Not yet. Okay. Yes, for some. Okay, good. So it should start finishing for everybody soon. Some people are waiting to schedule a job. Yeah. So this is the beauty and the horror of the cloud, in that it can do anything for you. It'll just compute it, and you have no control over exactly how that sort of all kind of plays out behind the scenes on those VMs. There's probably some connectivity and whatnot, but it is nice that they are using some VM background that will do it for you, and you don't have to use all the horsepower on your computer. I'm going to keep moving, but I don't think that's an issue. It will keep running, and you will get this output soon. And I think actually you can just keep going and start designing your neural network while that runs a little bit, but you don't actually have to. I'm just going to talk about it for a second. The next step that we would do is move on to the neural network classifier. And when you click on that, you will see a bunch of information here, but I want to point out that on the 3 dots at the top right, there's an option to switch to Keras expert mode. And basically this answers the question from before. So Edge Impulse has these pre-made blocks that you can sort of like add layers, drag them around, sort of figure out graphically what you want your neural network to be. And you can also use the default like optimizer and type into the things at the top what training things you want. And for today, we're just going to leave it as is. That should actually work decently well. But if you switch to expert mode, you also will get all the raw TensorFlow code. And so you can actually go in and design a model in TensorFlow exactly how you want, pick up the right optimizer that you want, and fully customize it and go as deep as you want. So if you have experience in machine learning and you want to fully customize everything, you can totally go ahead and do that. If you don't, you can just use the blocks. And if you're new to TensorFlow and you're trying to learn about it, I think what's kind of cool is if you screenshot the one mode and the expert mode, you can actually start to see like the direct parallels of a reshape layer is written as this in TensorFlow, and a 1D convolution with pooling layer is written as this in TensorFlow. And you can start to see sort of exactly what the pairings are, which I think is actually kind of nice and is helpful. And you can also see that the optimizer they're using, if you have these default settings in there, you'll see like the default optimizer coming down here and sort of what optimization they're doing. And as you want to dig into those, the TensorFlow documentation is actually quite great. And so if you look up these various functions, you will start to dig into a little bit more on the learning. Would the custom block fit if I made it very large? Not necessarily. And so that is actually one thing to keep in mind. That was, I think the next slide was literally my first slide was you can do whatever you want, use TensorFlow, blah, blah, blah. Warning, 1, make sure it fits, but 2, make sure it's supported by TensorFlow Lite Micro. So you can add any block you want, but TensorFlow Lite Micro only supports a subset of TensorFlow Lite, which only supports a subset of TensorFlow. And this is because the micro team needs to write optimized kernels for every single hardware backend that they support for every single kernel, right? And so they have to like really get things fully optimized down so that they'll fit on a microcontroller. And so they don't support everything. And there was a conversation, I don't know if it was there was a conversation the other day on one of our various communication platforms that we're talking about recurrent neural networks. And I know for a while, those were not supported. LSTMs were not supported by TensorFlow Lite Micro, but I do know that like we taught a course on this at Harvard, and one of the students actually manually made one. So he sort of like, recurrent neural networks have this sort of like the output of one is back into the input of another. And so he did that manually with like a for loop. And so he just used a simple model for the inside and then like did a for loop and was able to do it. So there are lots of workarounds you can do to try to create any sort of custom thing you want. And I also know that Pete and the TF Lite Micro team are working really hard to support as many things as possible. And so they will start to do that. And also, by the way, as you go through this, I think there's a thing where it will say roughly how big it thinks the model will end up being. before you start. And so you can start to figure out exactly what it will fit. And this is also dependent on your particular hardware, right? So each piece of hardware has a certain amount of memory, but we'll talk about this in deployment. The good news about Edge Impulse is that you can kind of just like go back, change one value and click, rerun again, and it will sort of run through the whole thing and try to do it for your smaller model. How do you get to the expert mode? So when you get to this screen, you see these 3 dots up in the right corner. If you click on that, there's a switch to expert mode, and there's a conversation around different kinds of classification. Yeah, there's a lot of nuance to neural network model design, and I'm not going to get into all of it today because, again, it's one of these things where it's like, go look at the field about what is everyone using today for the exact super awesome thing, but for just proving that things can work and for your first starts. Convolutional neural networks work great for images, recurrent neural networks work great for audio, for things that need memory. But honestly, like for a lot of this TinyML, you can get away with really simple models. And in fact, you have to use really simple models to get it to fit on device. So it's more of a game of how can you compress your problem into something that's simple enough that we can use a simple model for, and not how do I design the world's greatest model. And there's probably a lot of work that can be done for really good models that will help things work well. So with that, I wasn't going to change the model very much. We're just going to use one of these convolutional models because remember, we pre-process things into this MFCC, which is basically an image. And so we're just going to use these nice simple image 2 convolutional layer models to get some features from our audio and try to classify it. And so you can just click start training and it will go. So hopefully by now the feature generation has finished and you can click training, which will then again launch another cloud job, which will take a little while. So hopefully everyone is sort of there. And hopefully the training doesn't take too long, so we can play with it before we start to run out of time. How are people doing so far with all those cloud jobs? Are they sort of, have you been able to get through feature generation? Have we launched training? Maybe unclear. Yes. Launch training. Great. Okay. Perfect. So that'll take a little while. You do not have to split the data into training and test, because if you recorded with that automatic split feature that we did before, it automatically split it for you, which is pretty great. So you should already have 80% training, 20% test. Some people are already done with training. Some people are getting very lucky with the cloud, and some people are getting very unlucky. Apologies. Those of you that are already done with training, go buy a lottery ticket. Those of you that are still generating features, don't today. But as it's training, I'll show you what basically is happening. Is what you're going to see is there's going to be a bunch of training runs that happen. And remember, I said for training, you're going to give it a batch of data. It's going to train through it, and it's going to test it, and then try to update the model. And what you're going to see is you're going to get some loss, some accuracy, so validation loss and validation accuracy. The loss is some metric of error. The accuracy is just what percentage of them were correct. And you should see that the validation accuracy is less than the training accuracy. And this makes sense, right? Because we're actively training to improve our training accuracy. And then we're using this validation or test accuracy to make sure that we're learning something that generalizes beyond just the training set to also work for the test set. And if you get something that is you might get something that's in the 80s or 90s. I think somebody got 100. That is crazy, and the real test will become when we deploy, which is that it might work 100% on the actual training data, but if you have a small enough amount of training data, it might have kind of just memorized the training data and not actually generalized. And so this is why it's important to have a decent amount of data, but we'll see. And the whole point of this is to sort of explore and see what happens. And hopefully it works okay. And then when it's done, what you'll see is you'll have the final accuracy will come up across the top, the final loss. You'll get this accuracy breakdown, which is this confusion matrix. And there's 3 classes here, but the simpler version of the confusion matrix for 2 classes is basically along the diagonal, you have the answers that were predicted to be the thing that they are. So in this case, if we just had like yes and no, the top left is the model said yes, and it was a yes. And then the bottom is the model said no, and it was a no. And the error is the false positives and negatives are off the diagonal when the model and the actual didn't match. And so this was, the one that I ran last night on my very small amount of data. And you saw that like every time it thought it was a no, it was a no. And unknown and yes, it had a little bit more trouble. There were some errors here where it thought like unknowns were no's and yeses were unknowns and things like that. But it did okay on that training data. It turns out when I deployed this, it worked not as well because I didn't have enough data, but whatever. And again, you have this feature explorer, but now instead of just labeling it like yes, no, unknown, you also have the ones that were correct and incorrect. And what I thought was really cool about this was that you can actually click on an individual sample and you can listen to it, and you can click view sample to go to the actual file. You can click view features to go to the actual features. And so if you had a very large thing, or just in general, if you were just trying to dig in a little deeper to understand what went wrong during training to run it again, you can sort of click and explore and start to, get some insights. And for those of you that have less accuracy, don't worry. You might actually have something that generalizes better to the real world, even if the accuracy is worse in test. And remember, we only collected like 30 or 40 samples of each one. That is not enough for a real world deployment. It's just enough to play around with it. And it will be interesting to see how well it works. And you can always go back and add more data and try this again. And don't worry about it. This was just sort of learning the process and sort of exploring it. So at this point, your training is probably still running in the background, or it's done. But what you then have is there are a bunch of, we have now though essentially, finished our impulse. So we've done our data acquisition, we've done our pre-processing, designed and sort of trained our model. And then what we have to think about is deployment challenges and opportunities and a little bit of testing kind of stuff. And so what I'm going to, how do you check for overfitting, underfitting? Okay, so one thing you can know about overfitting, and there's a lot of tools in Edge Impulse, so there's probably a really good graphical tool, but like, even if you're not using Edge Impulse, one really quick thing to note is that if your training accuracy is like 100% and your validation accuracy if your training accuracy is going up and your validation accuracy starts going down, that means that you are just like memorizing the training data and not actually generalizing. So often when people train, they start to look at those training validation curves and you want to see them both sort of going up. And as soon as validation accuracy starts going down and training accuracy is going up, you have crossed into the point of overfitting, and you should stop training, or you should collect more data, et cetera. So that's like one really, really good quick check. And that's Edge Impulse agnostic. But they also have a lot of tools where you can, but anyway, yeah. I'll see if somebody else actually in the chat has some thoughts on some cool tools that they have, because they have more tools than I've had time to explore. It's a really cool platform. But while training runs for some people, I wanted to talk about deployment challenges, right? And so when we're going to a microcontroller, it's, super low power, super low bandwidth, super low cost, but there are trade-offs. Like, it is not a perfect system. And as people were mentioning before, memory is a real problem, right? Microcontrollers run a little bit slower than computers, but they have a lot less memory. In fact, this was just sort of a slide that Vijay had put in the edX course. He was saying that, a microcontroller is about 10x slower than a standard laptop or desktop, but it has, 10,000 to 100,000 times less memory. And so we're very constrained on the size of models that we can put on a lot of these microcontrollers. But there are actually a lot of recent microcontrollers that are being developed that have more memory and more storage, but this is still something you actually really need to consider. And this is particularly problematic because if you look at the size of AI models, they're exploding. Like GPT-3, which does this general purpose speech recognition, is huge. It's like billions or trillions of parameters. And so it'd be like gigabytes on disk. So for these embedded systems, we need to use simpler models and we need to compress them. And I think this also comes to a point of like, we can't yet fit, general purpose speech recognition on a microcontroller, but we can use a simpler model to tell apart a couple of keywords. And this is, I think, the really important thing you have to remember about TinyML is that it's most useful when we're using it for a very specific use case where we want to really specifically find one thing, and we want to shrink down data to signals. So whether that's, anti-poaching, so instead of just sending audio, we're going to send a ping, an alert, whenever we hear a gunshot, right? And so that's a very specific use case of audio detection, and it's just sending this one little thing, and we can just listen for like a gunshot noise. And these are the kinds of use cases where TinyML is at its best. As you move to cell phones or slightly larger devices, you can get away with, slightly larger models, et cetera, et cetera, et cetera. And so there are always these trade-offs, but we're getting better at compressing models. We're getting better at finding smaller models that do really cool things. And so maybe one of you will figure out how to get general speech recognition onto an Arduino, and then you'll win a Nobel Prize, and it'll be great. So go for it. But in terms of compressing models, there's also something we often do, which is called quantization. And this is generally done on most of the TinyML models. And the idea here is you can reduce the precision of the numerical representation that you're using, which can lead to a smaller model and faster computation. This is also important because some small microcontrollers don't support certain numerical representations. And for those of you that know a little bit less about computer architecture and these various precisions, what I'm talking about here is floats versus ints in particular. And so on most computers, you can represent a decimal number as a floating point number. That's the general representation. And I just like put the max and min in the corner. It can go from like, 1e negative 38 to 1e 30. I mean, huge range. And it takes 4 bytes per model parameter to represent a float. Instead, often a lot of times in machine learning, people actually will represent this float with an 8-bit integer. So that's only 1 byte. So we have 1/4 the size. But now we can only represent numbers between 127 and negative 128. So we've drastically compressed the representation power. The good news is most neural network parameter things. Oh, I forgot to add an image of that. But there's one in the edX course at some point. We took a snapshot of a neural network model, and like the vast majority of the values were between like -1 and 1, all the decimals. And so you can really actually compress the neural networks down into these less accurate representations, and things work really well. Oh, and it seems like in the chat, you did need to increase the sample size to 2 seconds, and that was my mistake, maybe? Okay, sorry. I thought that looked weird. Go see the chat. There might be a trick to improve your model. But anyway, this quantization, of course, if we were compressing our numbers, it does actually make things less accurate. But it turns out with neural networks, the accuracy drop is actually pretty small. It's like, for a lot of models, it can only be a couple percentage points, and you actually end up with something really great at the end. And this is some magical, mystical property of machine learning, in that it's very resilient to very small errors and very small changes. And in fact, actually, the model version that you are using is an int8 quantized model. So if you look at the top of your training, it by default quantizes it to int8. You can actually click on that dropdown, and you could open up the unoptimized float32 version, which is 4 times as big. And you can see if your accuracy is different. Probably for our small amount of data, you will find that it is very similar. But when you do very large models with large amounts of data, this actually can have some amount of impact. But it is a good trick that we almost always use on microcontrollers to just get everything smaller. And there's some really interesting research out there for those of you that are really interested in computer hardware in terms of quantizing to even smaller values and doing crazy different kinds of schemes, and how that trades off compute speed and accuracy and whatnot. Because if you do quantize at some point, you do have to unquantize at the other point. And if you use lots of different sizes, there's like lots of complexity there, but there's some cool research in different ways to sort of compress these neural networks down. And that's our convert model step, basically, because most of these microcontrollers want a quantized model. And we get that for free with Edge Impulse. We don't even have to think about it or worry about it. You just get this int8 thing that just comes right out, which is pretty great. So I really, again, that's just a nice plus there. Another challenge for these microcontrollers is that we don't have an operating system usually running on them. We don't have Windows, Mac, even Android or iOS, which also makes it hard because most of these operating systems have tons of libraries and tons of applications that you can build things on top of. And so it's really easy to compile it for Windows or Mac or whatever, with many common libraries. Well, okay, sorry, let me take a step back. It is not always easy to compile things. I've had plenty of trouble compiling things on different operating systems, and there are generally tool chains that work decently well on a lot of them. For microcontrollers, this is much more complicated often, which is why TF Lite Micro doesn't support everything yet, because sometimes they have their own custom hardware architectures and we need to have optimized code that is designed for them. And so there's all these additional complications. The good news is between all the work that the TensorFlow Lite Micro team has done and the work the EdgeImpulse team has done, the deployment process is quite simple. As Marcelo was saying the other day, you can do a lot of custom work outside of EdgeImpulse, but EdgeImpulse is also really, really great in the end of the day for deployment because you can kind of just like click Arduino library and it will just build you an Arduino library. You can click, the Nano 33 and it will build you a binary ready to go that you can just like flash right on. You can click an NVIDIA TensorRT library and deploy it to a Jetson Xavier. And so it makes it really easy to just like one-click deploy things all over the place and not have to do a lot of work with this, which in other words could be actually quite challenging to make sure you can efficiently compile and deploy. Can you use your own assembled MCU board? Potentially. If you look, when we get to if you look on this screen, well, actually, hold on. When you click on deployment, that sort of screen will pop up. And if your board is currently supported by EdgeImpulse, you can probably one-click deploy it. I can't guarantee that I know exactly how to deploy to your board, so you should definitely look through their documentation. But you could absolutely try to use that today. I would also be interested if you deploy it to your cell phone and see what the difference is, because we did record with the cell phone microphone. But a cool thing about EdgeImpulse is you could actually record through your microcontroller board as well if it had a microphone. Right in the beginning, there was an option to, instead of record on your phone, record on a sort of supported device if it is supported. And then when you quantization, do you reduce the precision of floating point, or you indeed use 8-bit integer? You can do both. You could reduce to 8-bit float, but actually in this case, we often actually reduce to 8-bit integer. And so you do a rounding thing where you take the maximum value is the maximum 8-bit, the minimum is the minimum, and then you sort of scale and round everything in between two integers. And integer math happens to be generally faster on computers, and for some microcontrollers, floating point doesn't exist, and so you have to actually use integers. But before we deploy, there's the comment of testing. Yeah, it's 10:56. I only have 10 minutes left, technically. We're probably going to go a little over. Sorry, Mark. We're not going to cover testing today, but EdgeImpulse has a bunch of different tools that you can use to do it. And I included a little link here. When they released their EON tuner, I'll put that in the chat. What's really nice about that and some of these other tools is they allow you to like automatically search between different changes to model architectures and retraining your model and playing around with your data and stuff like that to really do a lot of really good testing flows for you to make it a bit easier to just optimize everything. So I would definitely suggest you take a look at a lot of that when you're doing big deployment things. But for now, we're just going to go to deployment. But I see a bunch of things in the chat. Is there a trade-off between speed and memory and accuracy? Absolutely, absolutely. If you will for sure have a more accurate model using floats. It will be 4 times as big. Sometimes if the difference is 1 or 2%, it doesn't matter. In other use cases, it might matter. And so this is actually like the real challenge you have to think about in terms of what are you deploying to, what is your use case? If it's just turning on your smart speaker and it happens to mishear you once and not turn on, you can just say it again and that's not a big deal. If it's your self-driving car, you probably don't want that to mistake, a car for not a car and crash. And so you might actually want to think about using the most accurate, biggest model possible in that instance versus maybe just turning on your smart speaker. And so that's where there's all these trade-offs. And that's why I think machine learning is a pretty exciting field to work in right now, because we don't know what the best model is for every problem. We don't know what the best preprocessing is for every problem. And we don't know what all the real trade-offs are going to be when you deploy things in the real world. And so it's a really open and exciting time to be exploring all of this, because the computer hardware is now good enough that you can train in the cloud and train quite quickly, and you can deploy things that work quite well in real time. And there's large data sets available that you can practice on, publicly available, and it's not super crazy to use the internet to crowdsource data sets in the meantime. So it's a really, really exciting time to be learning and exploring machine learning. So finally, on to deployment. Hopefully by now your model has finished training. I think it probably has. Again, you can deploy to all these sort of different things if you click on deployment. For the phone, there's actually just a shortcut to just build it on your phone. And before we actually deploy it on your phone, I wanted to point out that your phone is actually quite similar to your little Arduino setup that we'll hopefully get to you soon. You know, they both have the accelerometer, they both have a microphone, both have a camera. I cut off the last letter of camera and microphone. Good job, me. But your phone is has a lot more processing power in it than the Arduino. But what's cool about Edge Impulse is we can just, click the button on Arduino, deploy to Arduino, and we're going to click the button and deploy to phone. And so, if you didn't have your Arduino with you, or you were just working on your phone, you could just test it on your phone, and then you could, run it on your Arduino later. And I think it's a really nice thing about that platform. So to deploy to your phone, one of the easiest ways I found to do it is if you go back to devices or data collection and you click connect a new device and show your QR code, or you pretend you're going to record more data, it will bring back up that phone screen on collecting images, collecting audio, collecting motion. And you can instead just click switch to classification mode. This was a question from much earlier. And now it will start building your project, and that will take, a minute or two. And then it will start allowing you to do inference live on your phone. And so what it has then done is it has compiled the model and deployed it to your phone, and you're no longer using the cloud. The model is now 100% on your phone, and you're testing it on your phone, which I think is pretty cool. And so when that happens, so by the way, just go connect a device, switch to classification mode, let it build. So while it's building, what you're going to get out is a score for yes, no, and unknown, or whatever labels you used. And essentially what this score is going to represent, and it's going to be a sliding window. So it's sort of constantly outputting a score saying, what do I hear now? What do I hear now? What do I hear now? And it's sort of the confidence that it has of each of those different labels. And so and whichever one is the most confident will sort of show up here. So in this case, I was saying yes, and it was 87% confident it was yes. And I had it was like, maybe it's a unknown or no. And so as you go through, if it works really well, you should see the word that you're saying showing up in bold and showing up here. It might be quite transient and go away quite quickly. So you may have to say it like a bunch of times in a row to get it to work. And if it's getting it wrong, I'd be interested if you look down to see what's going wrong and what's happening. For me, it was messing up no and unknown a lot. And so when I was saying no, I was getting like 50, 50, 60, 40 with no and unknown, and yes was down at 0, but it was really getting confused. I think I just did a bad job not collecting a lot of unknown data. I'm sure if I went back and did more, but it worked really well on yes, especially when I hissed and like really enunciated that S sound, which is why I like yes, no, because usually even if it doesn't work, if you kind of just hiss at it, it will pick up the yes, and then you can at least say, okay, it's figured out something. I did all right. But give it a minute for everything to deploy, and then we can all test our models. And that will hopefully work a little bit for you. And hopefully that was like a fun way of, doing the whole tiny machine learning flow. And then we'll do a little wrap up, and then I'll pass it over to Mark. And yeah, as Marco said, once your model builds, try it out a little bit and post in the chat. Is it working? Is it not working? Curious. Hopefully it works for at least one of the words for you. And did I put that as my next slide? No, it's after the summary. Okay. And if not, my biggest suggestion is to go back and collect more data and do the fix that somebody was pointing out in the chat, which was to change, I think it was change the pre-processing to 2 seconds, not 1 second or 2000 milliseconds. Looks like some people's models are, how can I know when I should stop training my model? That's a good question. It's more of like a use case kind of thing. So you could train it forever, but at some point you would probably start doing that overfitting thing we were talking about before. So once your validation accuracy starts to go down, I would definitely stop training because then it's not generalizing anymore. If also there's a trade-off on just compute. So like, for example, if you're using your own computer, or let's say you're using some cloud service that has a limited amount of time you're allowed to use it for free, and then it starts to cost money. At some point, you're going to be spending too much money and you need to stop, but there's actually no known answer because it's very model dependent and data dependent, exactly how long it will take to learn in general. What does uncertain mean here? Uncertain means probably that, okay, so I think what's also going on is if none of the labels are over some sort of threshold, and I believe that threshold, I actually don't know what that threshold is, but I assume it's probably like 50%, 60%, something like that. It's just going to say uncertain because it's going to say that it's not confident in any of the answers. And so this is often, I guess we should add a step of post-processing. You can often post-process the output and say, if it's not confident in any, don't say that it's actually heard anything. Looks like for some people it's working okay, for some people it's not working great. Is there any tool to estimate the execution time? Actually, yeah. I think it was the training screen on the bottom, there's an estimate of the time for a particular hardware. So you can select like sort of which computer type you have on your board, and it will tell you how long it thinks it will take to run. This is actually a good point because some of the models can take a while. So like in the edX course, when we did the computer vision one, we actually cropped the image down really small so it wouldn't take up as much memory and it would be faster to run. How do you deal with overfitting and underfitting? Usually it's more data is often the best way to do it to a point, and then you want to think about different kinds of sort of training schema. But usually overfitting is that you have a bunch of training data that is like very similar and very perfect, and the real world is not. And that's usually your biggest issue on that. And so you would probably just want to go collect a lot more real world data. And underfitting is usually that it's just not doing a good job training. And so probably train it for longer. Or if you're really struggling with your particular use case, that's where I would start looking to the literature to see if somebody had come up with a really cool new model type that works really well, etc. Can I use Raspberry Pi to deploy and get away from the limitation of using TF Lite Micro? Yes. Raspberry Pi should support full Linux. And so I think it supports a full TensorFlow Lite, not TensorFlow Lite Micro. So you can treat it sort of like the mobile phone. So there are definitely ways you could go about doing that. And I think technically, if I talk to the TinyML Foundation people, they would tell me that that's not TinyML anymore. That's embedded ML or small ML, and you have to go to the microcontroller to pure Tiny. But yeah, you can totally use the Raspberry Pis to make things more useful. They will use a little bit more power, but yeah, you could definitely get around some of the limitations there. And you could also think about like a really cheap Android phone would also essentially be a Raspberry Pi and give you some more power to do certain things. So it seems like people are getting to try it, and it seems like for some people it's not working very well. For some people, it might be working decent on a message or two, on a word or two. Hopefully, the point of today was just to actually walk through the whole flow and give you a little background about what all the steps are and using all the steps. And hopefully now you feel more confident to go and explore and do it yourself, and can probably do much better with a little bit more time and a little bit more care in your machine learning data collection in particular, and then potentially model design as well. So please post in the chat if you have any more questions, if you're having issues, if you found anything really funny about your model. Is there, if you did, a particular word, can you trick it with a certain word and get it to trigger, yes by saying less or something else? That would be pretty interesting. That if that works, by the way, you probably should have added that to your other words in the future. Add it to your unknown so that it doesn't get confused. And somebody's asking about the benefit of the Tiny experience. And I think that the benefit here is that we can deploy without using the cloud. Like, yes, it's going to be not as good of a model. And yes, it is, there are limitations, but you can get these microcontrollers, you can use them without any internet connectivity, you can use very low power, and you can leave them in the field. And I think you're going to see them more and more in a lot of IoT devices. So as you think about, having a smart fridge or a smart whatever that you're putting out, maybe a smart soil monitor out in the field, you could train it instead of just sending back, the value. It could start to learn and send back summary statistics. And you could also, somebody else pointed out, you could use wearables, absolutely. As you have to compress things down smaller and smaller into wearables, it's probably too power consuming and not small enough unless you start using like very small microcontrollers. And so I think there's lots of opportunities for really interesting smart things here, especially if they're doing, limited special case activities. And it totally makes sense for all that sort of stuff. You could probably get a very simple smart Fitbit type thing. And I'm pretty sure that a lot of those sort of devices, some of them are using some of that stuff probably now. So just a quick summary, and then I'll turn it over to Mark. We talked about machine learning. We talked about you provide labeled data with these answers. That's how we get the rules out. We talked about a neural network. We talked about both this like standard fully connected one, but being inspired by the brain, and then combining them together to get this full model. We also talked about convolutions being a really great way to filter images to try to get features. And then we worked through the Tiny machine learning workflow, collecting data, doing some pre-processing, training our model, and deploying it. And we talked about with collecting data, you really have to worry about bias, and then you have to make sure you have a separate test set. And there's lots of things to consider there. And I think, as Vijay said, a lot of the future of ML is about data sets. So really something to think about as you move forward. We talked about FFTs, spectrograms, and NFCCs being a great way to process audio. And my suggestion is to find the domain experts that are not in machine learning in your field and see what they're using to pre-process and analyze their signals and look at those, because that's probably a good pre-processing for whatever particular thing you want to do. We talked about training and the confusion matrix being a really interesting way to just sort of visualize and see where your errors are and what's going on with your test data. We talked about, we quickly mentioned quantization as an important thing. I'm just mentioning this because it will come up a lot as you deploy to microcontrollers that you need to do this. And so it's just something to be aware of. And then we talked about how Edge Impulse simplifies deployment, and we deploy to our phone. And hopefully when we send you, eventually, we can get all those Arduinos back in stock and everyone can get some. You can also try deploying to your Arduino, and you can or another microcontroller, and you can kind of compare and contrast how well they work and use them for different data collection and see what happens there. And then we talked about inference and seeing the score and whether or not it worked. And so I just want to, before I leave, I just want to note that this flow is what we use in the edX course. And if you're interested in learning more about a bunch of these things, one place you can look is there. Course 1 is more fundamentals. It's a lot of basic machine learning. So we mainly talk about designing and training models. So if you're more of a novice or no experience on machine learning, that could be useful. Lawrence does a large section getting into detail with some coding exercises around training and how it works. In course 2, we move to applications of TinyML. We talk about pre-processing to converting models. We still stay all in the browser. Everything's done through Google Colab, which is free for model training. We'll do keyword spotting. We also do a person detection visual one as well in there, and an anomaly detection one as well. And then in the third course, we move to actually deploying to the hardware. And we talk about some of the unique challenges of our particular hardware. We go through a bit of the Arduino code as well, and we deploy a keyword spotting, a person detection. We actually also deploy one that uses both keyword spotting and person detection at the same time. So it is possible to put 2 models at the same time on an Arduino, which is pretty cool. And then we also do an anomaly detection one with some Bluetooth training connecting to the computer. And all these materials are open source and online. If you go to our TinyMLedu website, you can find links to all of this, and the edX course is free to audit for the videos as well, for a certain amount of weeks per unique email address. And yeah, go work on better data to get better models. I'm sorry if it didn't work, but I promise if you collect more data, it will probably work better. And yeah, that's all I got.
Super. Thank you, Brian. Thank you so much. And I told participants that you were an excellent, speaker, and it was really a wonderful lab session.
Thanks.
Yeah, don't forget that on Thursday we will have one more hands-on session with Marcelo. So if you missed some of the points, you will go through the same steps with Marcelo, right? So
yeah, and I just wanted to answer one more question in the
sure.
chat, which I think was talking about pruning versus quantization. And so pruning can be done in two ways. It's a different approach to simplifying a neural network. One, you could just remove nodes in your network that are not doing much. But there's another thing that is often done, which is that you only turn them off during training, which helps the model generalize because each node can't necessarily specialize because they can't rely on each other. And then you bring them back all of them back for inference. And so what ends up happening there is you don't actually shrink the model size, but it's another technique you can use. And we talk about that also in the edX course. But I will stop taking up all the time, and I will let Mark have some time to talk about the multilingual keyword spotting, which I think is a really cool, more advanced extension. And in terms of do we get recordings? Yes, I am going to try to post them as soon as I can. I have not yet gotten the one from yesterday through all of the administrative, bureaucratic stuff. But as soon as I can, I will run them through the system, get them up onto YouTube, and we'll post all of them to that schedule eventually, as fast as I can.
Super. Thank you so much, Brian.